Children, once again, welcome to Physics with Sanoop, Healing Medical Aspirations. Fluids. See, there are a lot of things that you have to study from the chapter Fluids. But trust me, you have to know only few things. You have to understand only few things to crack NEET 2024. See, there will be 50 questions in NEET question paper from physics, of which you have to solve only 45. By following these videos, see, you will be able to solve 40 questions. Okay? And see, you can expect 2 questions from the chapter Fluids. See, what are those important things that you should know from Fluids to solve the 2 expected questions? Okay, the first thing, see this one, that is the Pascal's law. See, when pressure is applied to a liquid at rest, it is transmitted undiminished to everywhere in the liquids. Means, see, we have got 2 cylinders of different cross-sectional area. Okay, and see, here there is a piston of area small a. Here there is another piston of area capital A. Okay, here we have applied a force small f over area A, so the pressure is F by A, small f by small a. Okay, the same pressure will be transmitted to this piston also, where the pressure will be capital F over capital A. Okay, so if if we apply a force small f at this piston, the force that will be acting on this piston capital F will be capital A over small a into small f. For example, suppose the area of this piston is 10 times of the area of this piston. So, in order to lift a 100 kilogram weight kept over this piston, you will have to apply only a force that is necessary to lift 10 kilogram. So, if you apply 10 kilogram weight here, 100 kilogram weight will be available here because this capital A over small a is 10. Okay, that is the idea of hydraulic lifts. Now see, this is a previous question, a simple question, a typical question. Okay, see, a hydraulic lift, hydraulic lifts and hydraulic brakes are based on Archimedes principle, Bernoulli's principle, Stokes law and Pascal's law. See, even though this is very simple, this is the type of questions that you have to expect for NEET. Okay, definitely the answer is Pascal's law. Now see the next beautiful, wonderful concept that you should know. See, what is surface tension? It is the tangential force per unit length, or force per unit length is the surface tension. So in order to find force, you will have to multiply surface tension with the length. It is also the potential energy per unit area. So to find the potential energy, you will have to multiply surface tension with the area. But the most important thing that you have to understand, see, the potential energy is possessed only by the molecules on the free surface of a liquid. What do you should understand? By free surface area, the area exposed to air. Okay, now see this one, a liquid drop. See, only the outer surface area is exposed to air. It's the free surface area. Okay, and the potential energy per unit area over the free surface is surface tension. See, what is the total free surface area? Means the area exposed to air. It is the outer surface area 4 pi r square. Energy per unit area is T. So, energy over area 4 pi r square will be 4 pi r square into T. Okay. And see, here we have an air bubble in liquids. Only the inner area is exposed to air, inner surface area. See, over the outer surface area, see, that is in contact with the liquid. So the energy is possessed here only by the inner surface area inside the air bubble. Again, the area is 4 pi r square and energy is again 4 pi r square T. Now see, we have liquid bubble in air. Liquid bubble in air means inside there is air, outside also there is air. Inner surface area is exposed to air and it is called free surface area. Outer surface area is also exposed to air. It is also free surface area. So the total free surface area will be 4 pi r square plus 4 pi r square, inner plus outer, that is equal to 8 pi r square, and the energy is 8 pi r square into T. Now children, see what would be the case when the pressure is applied from both sides. See, suppose pressure is applied upwards from the bottom and downwards from the top. You might be thinking that see, the sheet will become or sheet will remain horizontal. That may not be the case always. See, it will curve depending upon the excess pressure. See, if the pressure from the bottom that is acting upwards is more, then it will curve like this. Okay. And see, if the pressure acting from the top downwards is more, then it will curve like this. So what is the conclusion? See, the surface will be curved such that pressure is more always on the concave sides. So in a liquid drop or bubble, pressure will be more inside the drop or bubble. Okay. Now see, in this case there is only one free surface. So the pressure is excess pressure is Pi minus Po equal to 2T over R, where R is the radius. Here also there is only one free surface. The excess pressure is again, see, 2T over R, where R is the radius. Here we have got two free surfaces, inner as well as outer. Okay, so the excess pressure will be 4T, twice of this, over capital R, radius. Okay, that is the one wonderful thing that you should understand. Now children, see, this is a previous question and also a typical question. See, a soap bubble expands, the pressure inside the bubble is, see, pressure inside minus pressure outside, that is the excess pressure inside a soap bubble. Okay, that is equal to 4T divided by R, where R is the radius. And pressure inside the bubble will be, see, PO, pressure outside, plus 4T by R, and PO usually it will be the atmospheric pressure. Now as the bubble expands, what does it mean? Radius will increase. Okay, so when radius increases, this term will decrease and the pressure inside the bubble will decrease. Okay, even though it is simple, that is one of the typical questions that you should expect for NEET. Okay, this is the answer, decreases. Now another important thing that you should understand. See, bubble expands. See, the energy, potential energy of a bubble of radius R in air, that is 8 pi R square T. And suppose the bubble is expanded so that radius becomes n times. So this is the final potential energy and this is the initial potential energy. So the work done in doing so will be equal to the change in potential energy. In physics, change is always final minus initial. Okay, now see, 8 pi that we can take outside, R square also we can take outside, T also, then 8 pi into n square minus 1 into R square into surface tension. Okay, now see another wonderful thing. When a liquid drop is split into a number of identical droplets, okay, then the surface area will increase. So the potential energy will increase. So work must be done. So what is the work done in doing so? It will be equal to the increase in potential energy, and it is equal to increase in surface area into surface tension. When a drop is split into a number of droplets, surface area will increase. Okay, now suppose a liquid drop of radius capital R is split into small n identical droplets, each of radius small r. Okay, so the volume of liquid will remain conserved. So the volume of that single big drop will be equal to the total volume of all n droplets. Okay, so small r, or let us say capital R equal to n raised to 1 by 3 small r, that we will get. Capital R, this is equal to n raised to 1 by 3 small r, this we will get. Okay, now the work done will be, see, this is n into 4 pi r square is the total area of n small droplets, and this is the initial area of the one big drop. Okay, so this final area minus initial area will give you the change in area into surface tension will give you the change in potential energy, and it's equal to work done. Okay, now we have see 4 pi capital R square n raised to 1 by 3 minus 1 into t. Okay, this number of droplets usually it will be 8 or 27 or 64. Okay, like that, or say 1000. Usually that n will be a perfect cube. Okay, so that we can easily find this n raised to 1 by 3, right? Now children, we have a typical, beautiful, wonderful question. Okay, see, work done in increasing the size of a soap bubble. See, soap bubble has two surfaces, both the inner surface and outer surface. Okay, and each surface area is 4 pi r square, so the total surface area will be 8 pi r square. Okay, now the work done will be equal to increase in potential energy, means increase in area into surface tension. Okay, so W equal to delta U, that is 8 pi, then final radius square minus initial radius square. Final radius is 5 centimeter, initial is 3 centimeter. See, here we are doing in SI system, so this is 5 square minus 3 square. That centimeter, to convert it into meter, we will have to multiply by 10 raised minus 2. But here we have to convert centimeter square. So the conversion factor will be 10 raised to minus 2 whole square, means it is 10 raised minus 4. Okay, so 8 pi, then final radius square minus initial radius square. This is the conversion factor, and the surface tension is given as 0.03, that we can write 3 into 10 raised minus 2. Okay, now see, you must be knowing this 5 square minus 3 square is 4 square. Okay, now see, in all the options there is pi, so you please do not touch on this pi, keep it as it is. Then 8 and this 3, 8 into 3 is 24. See, you will be never asked what is the answer. See, we have 4 options. See, you have to find, see, which among these 4 options is the correct one. Okay, so you can approximate, always you can go for approximation, right? So this 8 into 3, this 3 into 8 will give you 24. When that, see, 24, you can take it as 25. Okay, and see, here we have a 4 square, take 1 4 out of it, multiply this 3 into 8, take it as 25 into 4, so it will be 100. Okay, 100 into 10 raised to minus 6 will be 10 raised to minus 4. Okay, and 1 4 will be remaining here into pi, 4 pi. So 4 pi into 10 raised to minus 4, or we can write 0.4 pi into 10 raised to minus 3 joule. 10 raised to minus 3 joule is millijoule, so 0.4 pi millijoule. Okay, so 0.4 pi millijoule. This is the correct option. Okay. Now children, we have another beautiful, wonderful question. Okay, a mercury drop of radius 1 centimeter is sprayed into 10 raised to 6. It's again a perfect cube. Okay, 10 raised to 6 drops of equal size. The energy expended in joules. Okay, the surface tension of mercury is given as 460 into 10 raised to minus 3. Okay, cool down, relax. Okay, now W, this is equal to 4 pi r square. Then n raised to 1 by 3 minus 1 into surface tension. Okay, 4 pi I have written here. And the radius is 1 centimeter, means 1 into 10 raised to minus 2 meter. Radius square we have, so whole square. And this is, see, n raised to 1 by 3, n is 10 raised to 6. Whole raised to 1 by 3 will be 10 raised to 2, means 100. 100 minus 1, that is 99. Okay, and this is 460 into 10 raised to minus 3. Okay, now let us do one thing. Okay, now if you take this is 460, see, you can write 460 into 10 raised to minus 3 as 0.46. Okay, and this 100 minus 1, that you can take as 100 itself. Okay, 100 into 10 raised to minus 2 whole square, 10 raised to minus 4. Okay, 100 into 10 raised to minus 4 is 10 raised to minus 2. So there will be 10 raised to minus 2. And what remains? That is 4 pi. Okay, now see this 0.46 you can approximately take it as 0.5 into 4. That will give you, see 0.5 into 4 will be 2 into pi. Okay, it is approximately 2 into 3, that is 6. Okay, so 6 into 10 raised to minus 2. 6 into 10 raised to minus 2 is 0.06. Okay, it is an approximate value. Okay, so you have to choose the answer which is closest to 0.06. Here we have 0.057. So this must be the correct choice. Okay, children, the next important thing that you should know is capillarity. Okay, now this is the expression for capillary rise. 2t cos theta over r rho g. That small r is the radius of the capillary tube, rho is the density, t is the surface tension, and theta is called the angle of contact. Okay, now this cos theta by small r, cos theta by small r is the radius of the tube. It can be replaced by 1 by capital R, where capital R is the radius of the meniscus. Okay, now here see small r by capital R is cos theta, and see we can write cos theta by small r equal to 1 by capital R. This you should know. Okay, now let's try an example. Two capillary tubes A and B of diameter 1 millimeter and 2 millimeter respectively are dipped vertically in a liquid. If the capillary rise in A is 6 centimeter, then the capillary rise in B will be. Okay, this capillary rise is inversely proportional to radius of the tube. See, for the tube B, for the second tube, the radius is 2 millimeter, twice of the radius of the first. Okay, capillary rise is inversely proportional to radius. So when the radius is doubled, capillary rise will become half. Okay, so in the first tube, capillary rise is 6 centimeter. So in the second tube, it must be half of it, that is equal to 3 centimeter. Okay, now an important thing that you should understand in this case is, if the capillary tube is of insufficient length, means in the example that we have just discussed now, see the capillary height in the first tube, capillary rise in the first tube was 6 centimeter. Suppose the length of the capillary tube above the liquid surface is only 4 centimeter. See, the capillary height is independent of the length of the tube. It depends only on the radius. Radius we have not changed, but the length of the tube above the liquid surface is only 4, but the usual capillary rise is 6. Then what happens? You may be expecting the overflow like a fountain, but it never happens. See, in such cases, the liquid will rise only up to the brim of the tube, up to the top end of the tube. Now children, see we have a question based on that. Water rises to a height h in a capillary tube if the length of the capillary tube above the surface of water is made less than h. Okay, then water rises up to the top of capillary tube and stays there. Okay, that is the correct option. Now let's try the other options. Water rises up to a point a little below the top and stays there. Water does not rise at all. Water rises up to the tip of capillary tube and then starts overflowing like fountain. No, only the first option is correct. Now suppose this system means a liquid in a container and a capillary tube is held in it vertical, and this system is in a gravity free space, means just like in a spaceship or in a freely falling lift. Suppose a lift falls freely under gravity after this cable breakdown. Okay, then there is no acceleration due to gravity inside such a lift. In such cases, see the capillary height, in the expression for capillary height, this G comes in the denominator. When there is no G, or when G equal to 0, see we expect an infinite capillarity. Okay, or capillary rise will become infinite. That also never happens. In such cases also, the liquid rises only up to the brim of the tube, up to the top end of the tube. Okay. Now let's try a question. A 20 centimeter long capillary tube is dipped in water. The water rises up to 8 centimeter. Okay. And if the entire arrangement is put in a freely falling elevator, the length of the water column in the capillary tube will be 20 centimeter long capillary tube. Okay. What I have told you, see it in a space, or if the system is kept in a space in which there is no gravity, see the liquid will rise up to the brim of the tube. Here we have a 20 centimeter long capillary tube, so it will be up to 20 centimeter, right? Okay children, what you should know more in this chapter? The important thing, that is the equation of continuity. When an incompressible fluid, it is nothing but a liquid, is flowing through a pipe of non-uniform cross-section. Now the product of area and velocity of flow is constant everywhere over the length of the pipe. Means AV equal to constant, or let us say A1 V1 equals A2 V2. Okay, it's called the equation of continuity. Now see, we have a typical example here. An ideal fluid flows through a pipe of non-uniform diameter. Okay, the maximum and minimum diameters of the pipes are 6.4 centimeter and 4.8 centimeter respectively. The ratio of minimum and maximum velocities of fluid in this pipe. Okay, see we have A1 V1 equal to A2 V2, or area into velocity is constant. Okay, see if it is cylindrical or if it has a circular cross section, then the area is pi d square by 4. Okay, where d is the diameter. Okay, this is the area and this is the velocity. So pi by 4 is constant. So let us say V proportional to 1 by d square. Okay, so V1 by V2, as it is inversely proportional to square of the diameter, we will have d2 by d1 whole square. Okay, diameters are 6.4 and 4.8. Here we have d2 by d1. So it will be 4.8 by 6.4. It is 48 by 64. As it is a ratio, you can take it as 48 by 64 and you can divide easily by 16. So it is 3 by 4 and its square will be 9 by 16. Now the velocity is maximum where the area is minimum. We have to find the ratio of minimum to maximum velocity and it is 9 by 16. Okay. The next thing that you should understand in this chapter is Bernoulli's principle. Okay, P plus half rho V square plus rho GH is constants. Okay, see everywhere along the length of a pipe in which there is a steady flow. Okay, now see we have this P by rho G, it's called pressure head, H is called gravitational head, and V square by 2G is called velocity head, and all these are having the dimensions of height. Okay. Now children, this is a previous question and this is a typical question. Okay, a wind with a speed of 40 meter per second blows parallel to the roof of a house. The area of the roof is 250 meter square. Okay, assuming that the pressure inside the house is atmospheric pressure, the force exerted by the wind on the roof and the direction of the force will be. Okay, see we have to apply the Bernoulli's principle, P1 plus half rho V1 square plus rho GH1 equal to P2 plus half rho V2 square plus rho GH2. Okay, see when we take 2 points, one just below the roof and the other just above the roof, see the height or the difference in height of these 2 points will be just the thickness of the roof. Okay, just the thickness of the roof, that is negligible. So from a reference level, height to this point which is just below the roof and height to this point which is just above the roof are equal. Okay, so H1 equal to H2, that is I have written here H1 equal to H2. So this rho GH1 will be equal to rho GH2. The air just below the roof is at rest. See, I have taken the point just above the roof as point 1 and a point just below the roof as point 2. So at point 2, air is at rest, V2 equal to 0. And point 1, above the roof, see air moves with a velocity 40 meter per second. That is the speed of the wind. Okay, so V2 is 0, so see this term will vanish. Okay, and we have P1 plus half rho V1 square equals P2. So P2 minus P1, that is the excess pressure acting below the roof and it acts upwards. So the resultant force will be upwards. Okay, so excess pressure P2 minus P1 equal to half rho V1 square. Okay, that will be acting over area 250 meters square. So the pressure is, the force will be half into, density is 1.2 kilogram per meter cube and velocity is 40 square and we have area 250. Now we have this 250 and take 4 from here. 4 into 250 will give you thousands. Okay, what remains here? 400. Okay, this 1.2 by 2 will give you this 0.6 and 0.6 into 400 will be 240. Okay, 240 into 1000 will be 2.4 into 10 raised to 5 Newton, that will be acting upwards. Okay, so 2.4 into 10 raised to 5 Newton, that will be acting upwards. Option B is the correct choice. Children, next thing in this chapter, that is the speed of efflux. See, we have a container in which there is a uniform or homogeneous liquid filled up to a height h, capital H. And see, we have punched a hole at a depth small h from the free surface of the liquids. Then the speed with which the liquid comes out of this hole is called the speed of efflux. And it is V equal to root of 2gh. Okay. Now see, we have a typical example here. A liquid is filled up to a height of 20 centimeter in a cylindrical vessel. The speed of liquid coming out of a small hole at the bottom. Okay, and that is the speed of efflux, and we have the formula V equal to under root 2gh. Okay, g is given as 10 meter second raised minus 2. So 2 into 10 into height is 20 centimeter and it is equal to 0.2 meter. So we will get 2 meter second raised minus 1, that is the speed of efflux. And now see, the next thing in this chapter is terminal velocity. Okay, see, this is the expression for terminal velocity, and the most important thing is that the terminal velocity of a body falling through a viscous medium is directly proportional to square of the radius. Okay, see, this eta is the coefficient of viscosity, rho is the density of the body that is falling, and sigma is the density of the medium through which the body is falling. Now children, we have a typical question. Okay, see, two equal drops of water are falling through air with a steady velocity v. If these drops are coalesced, what will be the new velocity? See, usually there will be 8 droplets or 27 droplets or 67 droplets, like that, perfect cube. But here we have 2 droplets combined to form a single drop. Okay, see, when n identical droplets combine to form a single drop, the radius of the resulting drop is given by capital R equal to n raised to 1 by 3 small r. Okay, here we have only 2 droplets, that is n equal to 2, so r dash, the radius of the resulting droplet will be 2 raised to 1 by 3. Okay, now the expression for the terminal velocity is V equal to, see, the main thing that you have to keep in mind is that the terminal velocity is proportional to square of the radius. That is important. Okay, so V proportional to r square. So V dash by V will be r dash by r whole square. Means it is 2 raised to 1 by 3 whole square. So it will be 2 raised to 2 by 3. And we have 2 raised to 2 by 3 into V. Okay. See, only this much you have to learn from this chapter to crack NEET. See, by following this, trust me, you will be able to solve a 40 out of 50 questions without any difficulty. Okay, children, we have both free content in YouTube and also paid content in our mobile app. Okay, all of you prepare well and follow this channel. Thank you for watching and wish you all the best.